Okay, I think the other students will join us during the lecture, and can we start, Professor Vasenev?
Yeah, sure.
Thank you.
Nice to see everyone who is interested about the modeling urban ecosystems story. My name is Viacheslav Vasenev, and I'm associate professor here at the Department of Landscape Design and Sustainable Ecosystems, and also the coordinator of the Smart Urban Nature System. Yeah, we have a snowy weather and icy weather today in Moscow, so there are lots of people and machines cleaning the snow, and that's why it's a bit noisy, but I hope you can hear me well and also see my screen. So today I will try to give you an overview about the modeling urban ecosystems, which is of course a topic for let's say quite a long discussion, much longer than for 2 hours. So I will try to put the most important and at the same time the most interesting parts. And those of you who would like to get more information, I also will provide some sources of the additional information. Okay, by the way, I do not see, I see only my screen, so I do not see your faces, but I know you're there. That's why if you have any questions during the lecture, please put them in the chat or raise your hand. And probably Vlad will also inform me about upcoming questions if I don't see them. And at the end of the lecture, I will also leave some time to respond. So this is the lecture content. We will begin with talking about ecosystems and environmental modeling, basic concepts, so modeling ecosystems in general. And then we will talk about specifics of urban ecosystems and urban environment as the modeling case, modeling object. Afterwards, we will move to the discussion of the data for modeling, incoming data, which basically is the main factor of the model accuracy and of the possible implementation of the model results. And we will also discuss a conceptual framework and practical examples of modeling urban ecosystems. And at the end, I will show you a set of models for modeling soil, water, and atmospheric, mainly climatic components of urban environment. So this is more or less what we are planning to do in the nearest 1.5 or 2 hours, depending how fast it goes. So, modeling as a basic concept. Modeling is one of the most important, most widely used, and most widely discussed scientific tools. I think that almost any curriculum, starting from mathematics and ecology and physics, and ending up with linguistic or something very humanitarian, very likely has at least 1 or 2 subjects with the name modeling. For instance, in our curriculum for landscape designers, who are not really the researchers, much more people of art and let's say landscape studies, we have at least 2 or 3 disciplines related to modeling. For instance, I'm teaching the course on modeling urban ecosystems. And this is because modeling as a tool is a universal research method which provides lots of advantages. For example, if lab experiments or on-site observations, they allow fixing information which is ongoing, then modeling gives us an opportunity to observe the past and the future. So modeling expands the time scale of the research, and that's of course very important for environmental studies. For instance, we all now know about climate change issue, and we probably also aware of the risks of the +2 degrees climatic scenarios, IPCC scenarios, etc. But all these risks are coming from very complex and very powerful climate modeling. Similarly, the idea of the urban population increase and all problems coincided with this issue, with the lack of fertile soils and possible limitations in food, etc. They're also coming from complex social, ecological, economical modeling. So modeling as a research method which study an object by reproducing its features in a more simplified way as an analog or a fragment to the reality. And by this simplification, we limit the number of factors which we are not interested about, and we focus only on the factors which are the part of our research. For instance, here on the screen you see lots of pictures which are probably not clearly related to one another, a globe and kind of the 3D picture of an urban district and a beautiful girl, but they all are models as soon as they focus on one particular feature, for instance, the shape for the globe and the special organization for the 3D model and the beauty for the lady, and they exclude or neglect the other factors, and that's why they're useful. For instance, when we work with the globe, we have all the opportunities to see the shape of the continents and even to plan our trip from Africa to Australia. But at the same time, we would never analyze the elevation, for instance, because globe doesn't provide this information, or let's say we would not project the climate based on the globe, etc. So basically, I will conclude this long introductory slide with a quote by George Edward Fellman Box that all the models are wrong, but some of them are useful. So basically, model is a tool, and as a tool, they obviously are not free from some uncertainty, but at the same time, they allow projection of the parameters and factors which cannot be analyzed by the other ways. There are a huge variety of different models and even model classes. So model classes can be organized based on some criteria. For instance, by output, so by the information that the model yield, they could be qualitative or quantitative. For instance, the qualitative model will give us the mean, let's say the weather forecasting models are quantitative. We get the information on the temperature in degrees or on precipitation or something like that. But there are many models, for instance, related to the social science, which are more qualitative when we get there. For instance, an urbanization model can be also qualitative, since we have the land use change from one category to another, etc. We can have deterministic and stochastic models depending on the uncertainty factor and the factor of, let's say, temporal dynamics. By input, we can talk about static and dynamic models. So dynamic models, they consider the time scale, whereas static model, they analyze the interrelationship between the components, ignoring the time scale. So basically, for instance, the model of ecosystem which are not developing over time, but when we just take the cut for the particular time period. By the scope, a model can be descriptive or predictive. So predictive obviously means that we have some projections for the future, whereas descriptive models aim to analyze the complex relationships for the present or even for the past. And well, it's would be not correct to compare their quality or, let's say, the level of implementation. That depends on the research goal. If we want to analyze the weather for tomorrow, we need the predictive model. But if we want to understand why snow is going outside now, and what is the relationship with the atmosphere or let's say the water bodies, etc., then we talk about the descriptive models. And by application and functionality, we can talk about materialistic and ideal model. Of course, now we mainly work with the ideal model, so we don't have the model as some physical object. However, historically, materialistic models were the beginners of this tool. Let's say the globe, which we discussed before, or the model of the plane or of a tank, or the boat, which probably many of us played in the childhood. They're all materialistic. So basically, a materialistic model is something which exists physically, but also simplify the reality, whereas the ideal models are just in our minds, and they mainly are the schemes, equations, and some kind of schematic relationships. Yeah, so the ideal models can be mainly subdivided into two blocks, so the conceptual models and the mathematical models. Conceptual models are more qualitative. For instance, on the left of the screen, you can see the model of soil carbon cycle, or even more precisely the carbon turnover in the soil plant ecosystem. So here we see that there are different pools of carbon, active, slow, passive. We see also different players like soil microbiota, mesofauna, and also the fluxes, for instance, mineralization of CO2 or carbon uptake in humidification, etc. But we don't have the particular equations, particular numbers. So this model is good to illustrate the process, but not to quantify the process. And to quantify the process, we deal with the mathematical models. Mathematical models can look very differently. For instance, this is the photo I took many years ago when I was a student at the lecture of the theoretical physics that we had in Moscow State University. And of course, the models today, especially their interface, which is quite user-friendly, never look like this. But somewhere behind all beautiful pictures and schemes, we have the mathematical equations, and basically the level of modeling and the accuracy of modeling depends on these equations and also on the quality of data which are used to implement, to develop these equations first, and then to run the equations, to run the model for the particular processes and the particular cases. Ecological modeling. Ecological modeling is let's say, one of the directions of modeling in general when we deal with the modeling of environment, of ecosystems. Yeah, so we implement modeling for some natural environmental issues. And there are many. Again, I tried to organize them in a number of groups, but of course it was not easy because some of the groups overlap. There are models of soil, water, atmosphere. I will show you some of them in more details at the end of the lecture. And by meaning that this is soil model, a water model, atmospheric model, I mean that it mainly focuses on one of the components, but of course there are no models which can be only soil and which will ignore all the other components, since the idea of an ecosystem means that all the components are interrelated. For instance, at the end of the lecture, we'll discuss the hydrous model, which is a soil model which considers soil as a physical 3D body, but hydrous also and mainly is used to model the water and heat fluxes in soil. So although this is the model based on the soils, we still consider all the other components, and that's also true for the others. Like general circulation model, it's mainly about the atmosphere, but at the same time, some characteristics of soil, especially of land cover, they are considered as factors in this kind of model. Process-based models reconstruct some particular processes. For instance, in soil science and in ecology, modeling cycles of carbon, of nitrogen, of some nutrients, like for instance of potassium, are highly important. Carbon is one of the main directions of our research group, and we work quite intensively with different models of carbon, including some classical, like you see here, the century model, for instance, which was called century because it aims to reconstruct carbon turnover for 100 years period, but also for some others like ROTC or Rommel-Hume or some others. So these process-based models, they, as a rule, do not have the clear spatial resolution. Yes, so it doesn't really matter. Well, it does matter because the quality of the income data is quite important, but at least there are no limitations whether you use the model for a particular soil pit or for crop field or for a forest or for a region. So basically, as soon as you have the income data with the enough spatial accuracy, you can implement the process-based models for those. And there are many papers on century model, for instance, when it's implemented for particular plots like several square meters, or to golf courses of hundreds of hectares. So basically, the idea remains the same. Another group of ecological models are the land use change models. They are very widely used in landscape planning, for instance. There are lots of models on deforestation, on desertification, on urbanization, and we will discuss some of them. And there are many factors which can be considered. For instance, the CLUE model, which I refer here to, it is the land use change model which combines biophysical and social factors. So basically, it is the suitability model. It shows how land use can change. We consider the best suitability of the fertile lands for agriculture and let's say lands which are appropriate for forest growth, for the forestry, etc. But there are other, for instance, models which assume the anthropogenic effects on land use and that deforestation could be an issue. And following the concepts of ecosystem services, of sustainable development, of environmental economical interrelationships, we have many models which consider these two aspects, so which are focused on the economy of environment, economy of nature, and image globio and many other models can be an examples. So here we put an economical block in addition to the environmental part. We basically evaluate the economical quality of urban components. And of course, all these models can be used in different, let's say, in different groups. For instance, the land use change model and environmental economical models are used very often. So we first model the land use change, the deforestation, for instance, and then we can estimate the environmental economical costs or benefits of this land use change. And again, the image global model considers this approach. Okay, so these are the basic concepts of the modeling in ecology. Well, if we consider some classical examples, rather simple, but at the same time giving us some, not only names like the previous slide, but some understanding of what's going on. We can, for instance, have the classical ecological model of the population growth. Yeah, and this is the scheme which is very important, and at the same time which makes ecologists and well, basically all the people shall keep this in mind. This is the model of the exponential growth of the population. So you see that if we plot the population, the global population during the last let's say 10, 12,000 years, we see that in comparison to 2, 4, 6 and longer thousand years before Christ, the recent 100 years, especially the recent century, we obviously see the exponential growth. And ecologically speaking, it's very dangerous because the exponential growth doesn't have a clear threshold. So basically the population will increase until the lack of food or other resources will limit such growth. But this kind of equation, and you can see this equation in the frame, where n is the population and t is time and r is the coefficient of growth. Yeah, so basically this kind of equation so far describes the population growth pretty well. So for instance, today the global population is around 7.8 billion of people, and there are many resources and websites in internet where you can Google what is the global population, and you will get to the web page where the numbers are actually changing, yeah, every second. And this is not because physically newborn children are calculated, but this is an outcome of this, or I would say more complicated, but generally very similar to this model. So this is one of the classical things, but working very well also for the topic of our today talk. This is another one, also very classical, the Lotka-Volterra equation, which describes the relationships between prey and predators. It was developed almost 100 years ago for the relationship between rabbits and yeah, I'm not sure about the English term for this animal, but a predator for the rabbit in Canada, and let's say the wildcat, something like that. And yeah, you see that the population of prey and predators were strongly interrelated. So when the number of prey was too high, it was controlled by the predators who were killing them and eating them and decreasing their population in this way. But as soon as the population of the prey got to the lower position, then the predators were suffering from hunger and were also dying, and the effect of predators on prey was decreasing and the population of prey was increasing again. So basically the previous model and this model, the model of the exponential growth and the model of this sinusoidal dynamics, are the two typical examples of the development of ecological society, of ecological population. We can consider the exponential growth as a short-term dynamics, but at the end of the day, some limitation factors, which could be the predators or the lack of resources or something else, will control the population. So this is another classical example, and these are the equations again. N1 and N2 are the populations, and R and P are the factors which control their interrelationships between each other. Okay, how we implement these general ideas about models and modeling to the urban ecosystems. First of all, we start from the classical understanding of the ecosystem framework, ecosystem scheme, let's say. Also very classical and ecological, which can be obtained from what you see on the screen. So an ecosystem is a complex and open system which contains from the number of components. Usually these components are water, air, soils, lithology, and biosphere, the life phase, and all the components are interrelated. There are some, let's say, scientific terminological discussions, also more than 100 years old, between, for instance, an ecosystem and geosystem. So here you see that the life component is in the center, and basically an ecosystem and classical ecology, they focuses not only on the interrelationship between all the components, but on the interrelationship between the organisms and an environment. So they are biocentralized, let's say. The geosystem, from this point of view, are more democratic. So let's say all the components there are equal. That doesn't matter too much, but this explains why here we have the living organisms in the center of the scheme. This is an ecosystem in general. And this is an urban ecosystem, and an urban ecosystem means that the classical ecosystem framework remains, but is strongly affected by the anthropogenic factor. And the anthropogenic factor affects the ecosystem in lots of directions, in lots of ways, directly and indirectly. And all these effects can be summarized in terms of the environmental impact. And environmental impact assessment is the scientific and also practical directions which focus on this kind of effects, on the human effects on the environment. But at the same time, humans are also affected by an ecosystem, and these effects can be summarized in a concept of ecosystem services, which are the direct and indirect contribution of nature, of ecosystem, to human health and to human well-being. So all the time when we talk about urban ecosystems, we keep in mind these bilateral relationships. Human affects ecosystem, changes the ecosystem, sometimes dramatically and irreversibly, but at the same time, humans are affected by ecosystems and also could be beneficial, but could be quite negative when we talk about the health risks from environmental processes, for instance. Okay, are there any questions for this first basic part? And yeah, I don't know if there are any in the chat.
I have one question, sir, if it is possible.
Yes, sure. Let's go ahead.
I'm Karna Cyril from Samarkand State University. I work on the plant physiology and carbon flux measurement. So I need some advice and consultancy from specialists on modeling, carbon flux modeling. Do you have any experience with this?
Well, me personally, I mean, I personally work with the carbon fluxes and carbon stocks in soils, particularly in urban soils. And the models we use when we talk about the process-based model, it is the Rommel-Hume model, which some sort of similar to ROD-C, but with some specifics. And but this is not, let's say, my narrow sphere. I more work on the spatial modeling when we use different approaches like digital soil mapping. And at the end of the lecture, I will show some particular examples of the models we use, and maybe then we can continue this discussion.
Okay, thank you. Thank you.
Good. So let's continue. Now we can move to the second part, and we move from modeling, environmental modeling in general, to the urbanization specifics, because modeling urban ecosystems is different from modeling ecosystems in general, or let's say urban environment brings a number of specific cases and scenarios. This is kind of an starting point, an argument to deal with urban ecosystems and urbanization issues. This is a scheme coming from the United Nations World Urbanization Prospects 2018. And basically what we see on this graph is, first of all, it's an illustration of the exponential growth of population we saw before, just for a shorter period, and that's why it's less obvious, but still described with the exponential model. But what is also important, you see that during hundreds, and if we'll go a bit before thousands years, urban population was dominating. So more people were living in out of cities than in cities. However, just recently, starting in 2007, if I'm not mistaken, for the first time, the percentage of urban population got higher than of rural population. And likely this process is irreversible. So I mean, from now and further on, urban population will dominate. And when we talk about the increasing population, which is projected to get over 9 billion by 2050, according to the UN forecasts, up to 70% of this population will live in cities. So urbanization, urban environment become, let's say, very important issues for global and regional ecological studies and for ecological modeling as well. There is a discussion, what shall we consider an urban area? And here we also, as usual, we depend on the research task, but also on the incoming data. Usually there are two main factors, two main ways. First of all, and this is an approach more traditionally used by the statistical bureaus like also United Nations or FAO, Eurostat, etc. And they're based on census data. Based on the census data, we define an urban area considering the number of population, and this is the formal criteria, and the activity, the economical activity of the citizens, and this is the functional criteria. For instance, in Russia, a settlement is considered a city if the population is above 12,000 and 85% of the population are not involved in agriculture. So you see here we have both formal and functional criteria. But in different countries, these thresholds can be different. In China, the threshold is much higher, obviously, and for instance, in Denmark, this threshold is 5,000. So 5,000 is enough to consider the settlement an urban area, etc. So in addition to these national specifics, there is always, of course, the lack of legacy data to give a clear definition for some settlements. So there is no doubt that, for instance, Moscow or Beijing are urban areas, but there are many new settlements or just small settlements or dynamic settlements which have recently increased, for which such census data is not available, or it gets available but with a long delay. So from this point of view, quite often, especially for some special analysis, when we not only consider the whole area as urban or non-urban, but when we are working on its dynamic, we use another example, which is based on the special proxies. Proxy means that we do not have a direct, straightforward information on an area as urban or non-urban, but instead we have an access to some special data which can be used to qualify an area as an urban. For instance, the percentage of the impervious surfaces, of sealed soils, the percentage of the built-up areas of roads, etc. This is a very typical index. Depending on an approach, we can say that if a grid is more than 50% impervious, then we consider it an urban, or sometimes 25%, more or less, again, depends on the approach. But generally speaking, here urbanization is a function of the special proxy, which can be the land cover, the percentage of the impervious surfaces, or some vegetation index, like vegetation built-up index, or NDVI, or some other source of spectral information. Or, for instance, city nighttime light data, which I will illustrate to you a bit later on. So when we use this approach, we can map urban areas indirectly based on some spectral characteristics. These are the examples. For instance, this is an example of urban areas based on the census data, and this is the public cadastre map of Russia, which is available for any user. You just go to the internet website, which now I think is PKK5, or maybe now it's version 6 or 7, doesn't matter too much. And here you see for all Russia, and that was a huge work to do it, for all Russia, you can check any plot, like your countryside plot, for instance, your countryside house, or your courtyard, or your city. Again, it depends on the scale. And for each plot, you get an information where you have the land use category. So if you're not sure whether your area is urban or rural or forest, you can just go and check. This is the census data, because it doesn't explain why this area is urban or rural. It just gives you a clear definition. And of course, it's great when you have this opportunity, because it's a very straightforward way to analyze the land use and urbanization. But in terms of the spatial model, for instance, the use of such data is quite limited. And this is an alternative example, basically based on this special proxy on the night light index. And the main idea here is quite obvious, although I think it was implemented in a very smart and beautiful way. I sometimes saw this figure as just a decoration somewhere in the office. This is the mosaics of the Earth surface at night. Yeah, and you see that with different colors, we see the intensity of the night light. And of course, in urban areas, the intensity of nightlight is much higher than in the desert of Sahara or somewhere in the forests of Amazonia. And this is what we see here. So here, especially at the global scale, this is a very clear proxy of population density. And if we compare such satellites for a number of years, we can also see some dynamics. But at the same time, when we work the regional scale with this kind of sources, there are some uncertainties. For instance, I used this data. This data was generated by the GRUMP project, which is the Global Rural Urban Mapping Project for the Moscow region. And at this scale, there are some uncertainties and errors. For instance, all the roads with lightning, they are also considered urban, and sometimes the road's length can be like 100 kilometers, and it still will be considered an urban area, although in fact it's not. So depending on the scale, you can select this or that source of information and this or that definition of an urban area. Why do we think that modeling urban ecosystems is specific? Yeah, what is the specifics of urban ecosystem as a modeling object in comparison to natural or rural sites? Let's see some examples. First of all, urban areas are very heterogeneous. Yeah, they're very variable in space. They're very patchy. So basically, it's difficult to characterize urban ecosystem even of a comparably small plot, let's say 1 kilometer to 1 kilometer, by a single number. If we talk about some environmental parameters like soil carbon, for instance, because they are very diverse, they are very heterogeneous. Here you see the two plots, one from the natural, or I would say from the agricultural area, and the other from urban. They have a similar extent. Yeah, I think it's 500 to 500 meters, and maybe 1 to 1 kilometer. But you see that although a cropland is also quite heterogeneous, so we see some short distance variability due probably to different soil moisture, and we see even some different land use. But at the end of the day, the number of homogeneous areas here is maybe 5 or 10. But for the urban environment, we would have something like 100, because we have houses, roads, courtyards. They're all very small in extent, but quite diverse and with abrupt changes. So in this regard, for the spatial modeling, but also for the process-based modeling, urban ecosystem is a challenge. And that's why the incoming data is so challenging, and the density of sampling shall be much higher, etc. So this is one of the specific features to keep in mind. Another feature is dynamics. So when we talk about modeling, and you remember from the beginning of the lecture, we can talk about the static parameters and dynamic parameters. But even if we talk about static parameters, we still shall keep in mind that in reality, the ecosystems are changing, and any ecosystem is dynamic. Yeah, all the environment is dynamic, but this dynamic can have different drivers and different explanations. For instance, when we talk about a forest, yeah, it is dynamic, naturally dynamic, dependent on the climate. We can have the seasonal dynamics and perennial dynamic, but this dynamic can be described, projected, and considered. In urban environment, we have lots of stochastic, basically unexpected changes. For instance, renovations or restorations of existing green areas and stuff like that. So for those of you who do not read Russian, and I expect that most of you do not read Russian, what is written here is that it's a reconstruction of the park is ongoing, and this is the number of trees, 279, and shrubs, 4,000, and lawns, 4 hectares to be reconstructed. And this means that basically in a couple of years, sometimes within one season, the surface of the park, the combination of the land covers, the soil properties, the vegetation properties are completely changed. So basically, it's a new area, it's a new ecosystem. And of course, this rapid dynamic, something which is very typical for urban environment and also very challenging to consider in environmental modeling. Another issue would be multi-layerness. So basically, if we talk about modeling in 3D, yeah, in 3 dimensions, we shall keep in mind that whatever ecosystem we talk, we shall consider not only what's going on the surface, but also what is underneath. And in urban environment, underneath we have long residential history. Physically, this history can be observed from what is called the cultural layers. Yeah, here you see the excavations by archaeologists in the Veliki Novgorod on the big screen, and from Moscow on the left screen. And both Moscow and Veliki Novgorod are close to 1,000 years old. And during these ages, the residential activity, including the waste production and management and landscape and some crop production, etc., they all were resulted in accumulation of the deep cultural layers. Sometimes they can be 5-7 meters deep, and they are very interesting in terms of carbon, for instance. So this is one of the reasons why we work with them. But this cultural layerness is these cultural layers are kind of an illustration that urban environment is not only dynamic in the short term, like we discussed before when a park was reconstructed, but it also has a long land use history, even if its land use history is within an urban area. So this kind of land use history, residential history, shall be also considered and used in modeling. Otherwise, you lack the explanation of the sum of ongoing processes. Okay, yeah, this is just a more clear view on these cultural layers, and please consider that first of all you see the scale in centimeters, so this is 4.5 meters deep, and you also see that, for instance, in terms of carbon, the highest carbon concentration are at the depth under 2.5 meters. So some areas where we almost never get with the soil survey. And this corresponds to the 15th century, so to 500 years ago. This time passed long ago. Yeah, we don't have too much evidences about this time, but in terms of the modeling, in terms of the ecological modeling, these cultural layers remain, and they have quite an important influence on ecology today, for instance, as the sources of greenhouse gas emissions or as buffers for heavy metal pollution, etc. Okay, what else? Of course, we have a clear effect of anthropogenic factor as a crucial driver to be considered in modern urban ecosystems. Basically, all the time when we deal with urban ecosystem, we shall consider both direct and indirect human effects. And if directly, human changes environment by pollution, soil sealing, waste disposal, artificial soil constructions, urban greenery, etc. But the indirect effects by changing, for instance, urban climate, are still very important and shall be considered as the environmental factors. Okay, so this is the specifics of urban environment, urban areas as a modeling object. And we are more or less, close to, no, we still do not reach the half of the lecture, but let's say 40%. Any questions to this part? No. Okay, then we continue. And now let's talk what and how to model regarding the urban ecosystems and where to take the data for modeling. If we simplify the modeling framework in as far as we can, so make the most simple scheme for the modeling, from my point of view, it would look like this. So we have incoming data. Without incoming data, modeling is theoretical. Yeah, so theoretically we can describe the interrelationships between the components of ecosystems, but we can never quantify those, or if we quantify, we can never validate. So from this point of view, incoming data is the crucial point for any modeling. So we need incoming data to fit the model, to calibrate the model, and to validate the model. And this is one of the main incoming component. The other component, or the other important part, are the modeling parameters and assumptions. So basically the rules which we consider, because if you remember the very beginning of the lecture, modeling is always simplification of reality. Models are always more simple than the real life, and that's why they are more efficient to analyze the environment. And this simplification shall be done by some rules. And these rules are the model assumptions. So for instance, when we do the, let's say, some special modeling of carbon stocks, we assume that we talk only about organic carbon, and we do not talk about the carbon fractions. Or when we model the population growth, we assume that the urbanization will follow the logics and the patterns previously obtained, and nothing emergent will occur, or at least will not be considered, etc. So these kind of assumptions, rules, which describe the processes and our attitude to the modeling processes, is the second part of the model. Then we have the model itself, which is basically, again, it can look differently in terms of the interface, but at the end of the day, we have mathematical relationships statistically described, where we have the variables, parameters which we analyze, and the factors, drivers, which are the processes or the factors which influence the variables. And we describe those relationships through a number of equations. Usually we make some scripts to describe them in a more mathematical way. So all this is inside the model, and basically modeling is mainly these procedures. And at the end of the day, we get the model outcomes. So something that is the result of the model, something that we see on our screen, or send to the decision makers, or by publishing a paper, etc. And they could be assessments, maps, projections, etc. So we will use this model framework further on, and we will describe some case studies having in mind this model framework. But before going there, let's discuss each of the parts, and to begin with the income data. So the income data is basically the data without which the model cannot be fitted, and the income data distinguishes what are we modeling, or the model aims can distinguish what kind of data do we need. So depending on the income data, we can deal with different features of urban ecosystems and their components. For instance, soil properties, air temperature, concentration of pollutants in air, concentration of pollutants in water, etc., etc., etc. Numerous parameters of environment can be modeled. Then we can get some data on environmental processes, for instance, biomass growth, depending on the species, or on the age, or on the climate, or on something else, or air pollution as a process, so the number of pollutants emitted per time, per area, etc. Ecosystem functions and ecosystem services like carbon sequestration or water purification also could be the data needed for modeling, and also could be the model outcomes. risks like flood risks, or the percentage or the probability of the particular area to get flooded, or the pollution risks, the probability of an area to get polluted, or basically a probability that in a particular area the pollution concentration will be above the threshold, etc. And different kind of scenarios, possible ways of the model development. Like climate scenarios is the most clear example. So for instance, those of you who have some relationships with the climate analysis know about the IPCC climate scenarios, like IPCC IR scenario, which actually, for instance, considers this +2 threshold, that if we do not change our climate policy, we reach the +2 degrees with a probability of about 50% by 2050, etc. All the urbanization scenarios, like that urbanization can go this or that direction. Like for instance, here in Moscow region, we have the New Moscow project, which is basically the ongoing, very intensive urbanization in one direction, which was the result of the political administrative decision taken in 2012 to decentralize the Moscow area. And that scenario was quite not feasible, let's say 20 years ago. Yeah, 20 years ago, some other scenarios of urban expansion could be developed. So the scenario is the possible trajectories of changes, and they are also considered when we decide what to model. Where to take the incoming data? That's a crucial point for model developers, because for model users, it's also important, but sometimes when the model is already developed, we can try to adapt it for the data we have. But for the model developers, the lack of incoming data means that the model cannot be established. And from this point of view, the different sources can be considered. First of all, of course, we can obtain the data, let's say, with our hands, physically, from the field observations, from the surveys, and this works for some data which was never collected before, some new data or the conventional data, but for the new areas, etc. Another opportunity is to make an experiment and to collect some data from the experiments. Generally speaking, the observations and experiments are two main ways to collect data. They both are widely used, and the only difference is that with the observations, field observations, you can collect data, let's say, most typical for the current conditions. You cannot collect data on some extreme events, and sometimes you need the data for the extreme events to model, because model shall consider all the possible outcomes, and here the experiment is more appropriate. Like if we analyze the possible effect of heavy metal pollution on soil health, here in Moscow we don't have too high levels of pollution, and that's why with observations we cannot reach like thousands of ppm of lead or cadmium. But theoretically this is possible, and to know what are the possible outcomes, we shall make an experiment. So we shall just create such a concentration and see what outcomes can be fixed. When we need some historical data, let's say data from the past or the special data, then we can use scanned maps or some literature data if it has the clear georeference. But of course, most often now with all the possibilities brought by open data policy and remote sensing, we use the remote sensing data from satellites. There are lots of services and lots of data sources from free available satellite images, which can be used and which are used in models on very different directions. For instance, the Landsat images cover the whole globe and have the resolution of 30 meters. And the Sentinel images, they are available for just a couple of recent years, but they give a resolution of 10 meters. That's very accurate, even for urban environment. And they're all free of charge, by the way. Some commercial satellites, they provide information with the images resolution of 0.3 meters, 30 centimeters. And with this information, you can do more and more. So basically, remote sensing now is one of the most powerful sources of incoming data. What is the limitation of remote sensing is the temporal resolution, because as a rule we can get information almost for the whole globe, especially, but let's say once a month, or sometimes even once in several months, considering that the remote sensing data quality can be different. Sometimes the cloudiness can decrease the accuracy or some other reasons, or the shadows. So for some processes which are very intensive, like air quality, for instance, changes, remote sensing is not enough. And we need some data which characterizes these processes in a shorter period. And these data are coming from monitoring. Yeah, so basically monitoring is continuous observation of some parameter. And monitoring urban environmental data is ongoing in many cities in the world. Depending on the parameter, it can be very frequent, like several values per hour, or even sometimes several values per minute, depending, of course, on the equipment and the tasks. But generally, monitoring at a limited number of points is the source where we can get the information on temporal dynamics. And this monitoring data-based data sets can be an income data for dynamic modeling. So remote sensing combined with monitoring can provide a very strong data set for spatial and temporal model. And of course, depending on the scale, we can use information from the thinner or coarser resolutions. For instance, the weather predictions are based on the global models, which, like global circulation model, which are adapted to the regional model, and then the regional model can be specified for the particular city, like when we do with the urban heat island modeling, when we will analyze a bit further on, etc. This is an illustration of an air quality in Europe monitoring, which we, by the way, can probably try to assess. Can we do that? Yes. So basically here we can select a city of our interest in Europe, let's say Prague, Czech Republic, and we can see the concentration of the pollutants at today and yesterday. Yeah, the data is correct. And we can also see it for the roadside and for the background, so basically for more polluted and less polluted environments. And this is the air quality index estimated from 0 to 100. And if you go to the methodology, you can see more descriptions on how it's estimated, but it doesn't matter that much. So, and there are many other ways. So here in Moscow, we have Moscow monitoring with a similar functionality. In US, there is air quality in US, and it's not only about air quality. So basically, these or similar monitoring resources, they provide information for the incoming data for the dynamic processes. Okay, that was about the incoming data. Let's move to the assumptions. Assumptions, again, are the rules which limit or which create modeling development. Some things that we ignore or some things that we focus on, etc. What can be the assumptions? First of all, assumptions on model variables. For instance, again, those of you who have some experience in statistics, they definitely know some statistical assumption about the for instance, normality assumption. So we very often assume that the incoming data is normally distributed, and because this is important to implement many statistical tools like the ANOVA, for instance, or something else. Assumptions on the relationship between the variables. For instance, we can assume that the data is well approximated with linear regression, and then we can use a regression equation. Assumptions on driving factors. For instance, we can never, of course, consider all the factors, so we can assume that the factors which are not included in the model are negligible, and that's why we can exclude them. Assumptions on dynamics. So we can assume again that the process is well approximated by the linear or exponential or log normal equation, and they never can be explained with them perfectly, but we assume that this kind of approximation is relevant for the model purposes. Assumption of the scale. So what shall be the minimum grid cell? What shall be the minimum resolution? Like when we discussed before the climate modeling, for instance, when we talk about climate modeling at the global scale, we talk about 10 kilometers, could be 100 kilometers. But when we model climate within a city, we talk already about 500 meters, for instance, if it's the regional mesoscale modeling. And at the micro scale, we can go at more and more smaller distances. So at each scale, we assume that this scale is good for our purposes, so that at this scale, the minimum grid cell is homogeneous enough to be considered as an appropriate resolution, etc. So all these model assumptions shall be agreed in advance, so before modeling, and then considered for their uncertainty analysis and considered for the interpretation of the results. If we assume that the minimum grid cell is 10 kilometers, then the accuracy of the climate model in a city level will be probably too low. At the same time, if we assume that the accuracy we need is 1 meter, then it will be possible or very difficult to make such a model for the city areas. All the time we find some kind of a compromise, and all these compromises are organized in these model assumptions. Driving factors. Driving factors basically are the information sources, the variables, the processes which distinguish the parameter of interest. And driving factors are also obtained from the income data, but this kind of income data is especially relevant because we assume that changes of driving factor change the parameter of interest. For instance, when we talk about the land use model, land use planning, as we mentioned for the clue model, the driving factor can be the suitability analysis, can be the suitability of an area for the particular land use. And here some biophysical, like soil fertility or social economic variables will be the driving factor. So we basically say that if soil pH is 7, for instance, and the expected yield is 50 tons per hectare, then this area shall be used for agriculture. Otherwise, it shall be natural protected area, something like that. So this is the driving factor. We consider soil property and expected yield as the driving factor for the land use category. Another example can be the neighborhood factor. The neighborhood factor is a very classical example when we model land use change, which is not driven by some decision, I mean like governmental decision, but more independent. And neighborhood factor is very often used in urbanization modeling, It basically means that the likelihood of an area to be converted to urban is much higher for the suburban areas, for the areas which are in close proximity to existing urban areas than to some areas which are remote. So in the other words, it's much more likely that Moscow will expand to the nearest district than a new area or a new city will be developed from zero somewhere in the middle of the forest. So, and some components like cellular automata or machine learning can be used considering this approach. So basically, driving factors again are usually special. If we talk about the spatial modeling, some kind of information which determines the behavior and the value of the parameters of interest. And yeah, depending on the model structure, this could be the dynamic or spatial data or both. What are the model outcomes? So what do we want to see at the end of the model? Again, there are lots of options. Sometimes we can obtain some numbers. Yeah, this is again very simple classical example. When we have the regression model, we basically assume that this regression model allows predicting a number for known incoming data. We just put the incoming data in the equation and get some number. For instance, here you see the climate comfort index estimated by the Rayman model. Yeah, the Rayman model is a kind of the microclimatic model to estimate the physiological comfort from different climate, dependent on the environmental, but also on the human factors. And here we see the number, so basically the temperature which we expect. But if we would like to put it on the map, it's also possible. The model shall be organized differently by different tools with the GIS data as an incoming and map algebra relationships as the driving factors. But at the end of the day, we can yield the map looking like this, for instance. This is the urban heat island map based on the LiDAR data. Could be, again, it could look differently, but general idea is the same. Or could be the projection, like with the climatic scenarios. So we can see some projection for the future as a graph or also as a number per time period. This is what we can expect as the model outcome. Any questions for this part? No. Good. Okay. So far, so good. Now let's give some examples. Some examples of modeling urban ecosystems in general as a conceptual framework, and then modeling some particular parameters of urban ecosystems. First of all, the general model. Generally speaking, modeling urban ecosystem is quite a novel direction, and generally urban ecology, urban environment is probably more or less intensively developed since 1950s, 1960s, so not too long. And since the very beginning until now, modeling urban ecosystems deals with the searching for a balance between environmental and social economic blocks. In the beginning, and let's see here in the paper by the Professor Wegener from University of Dortmund in 1994, who reviewed some previous models as well, we see that the factors considered for modeling an urban area are almost mainly social economics. So we do not have this environmental biophysical parts. They are almost neglected. Yeah, this could be a model assumption. So we have here land use, housing, population, traveling, employment, and all the other social and economical factors, but we do not have urban environment, urban ecosystem, neither as a resource or as a place of life. Maybe just the land use can be a side factor. So this is kind of the starting point. And of course, since we are talking about modern urban ecosystems, this is not the situation which could satisfy the ecologists and urban ecologists. And therefore some dynamic, some development, some model evolution in this sphere occurred. This is a more recent model, UEM, by Professor Marina Alberti from Washington University in the US. And here you see that basically urban ecosystem is considered as a combination of biophysical module and social economic module, which have some mutual interrelationships on the ecosystem as a, let's say, special surface. So we have that for the social economic model, we see something similar to what we saw before: actors, markets, resources, etc. And the drivers are also related to socio-economic information, the demography, policy, technology, etc. But at the same time, we have the natural system, which includes climate, which includes biogeochemical cycles, including the carbon cycle, the hydrology, etc. So these two modules are linked through the land conversion and waste production and the use of resources. So natural ecosystems can be considered as a resource, like a resource of fertile soil, as a resource of clean water, etc. But at the same time, we have the socio-economic model, which distinguishes the production and consumptions, how much ecosystem services, starting from the food and ended up with recreation, the socio-economic component could consume and could produce, etc. So I would say that although this model is already 20 years ago, 20 years old, generally speaking, this concept remains relevant. Of course, the details can change and have been changed, but conceptually, bringing together socio-economic model and biophysical model works for urban ecosystems models. This is another model framework developed 10 years after by Dr. Stuart Pickett from University of Illinois. And here you see that the ecological component is included in all the other spheres. So basically here he presents urban ecosystems as an integrated social ecological system where we have land use, land cover, production, consumption, disposal, etc. And this description is from the publication of Pickett from 2011, where he also touched a very, I think, important case related to the modeling scale. So basically we can talk about the city scale, and then we depend on such data as remote sensing data, satellite imagery, etc. Or we can go to the more local scales and deal with some surveys, tree data, soil data, etc. Here are some examples of the urban ecosystem models. Again, I'm not sure that these names will talk a lot for themselves, but at the same time, generally speaking, the blocks, the categories are quite representative. For instance, the gravity models like DRAM, which probably were among the first ones, they relate urbanization to the employment location. So they ignore or almost neglect the environmental issue and have a clear social economical relationship. Employment, so people looking for a job, is the main factor for the labor migration, and labor migration is the main factor for urbanization. The market-based models, like for instance urban sim, they relate urbanization to the demand and consumption in land trend. So if people are looking for residence, and if this residence is affordable economically, then they settle, otherwise they do not. So that's kind of the urbanization, also based on the social economic factors. Programming-based models like polis, where urbanization is a function of optimal transport and establishment of costs. Again, here we have not only the residences, but also transport infrastructure, and depending on the optimization, also to be decided what we consider an optimal situation, the, let's say, configuration of the urban area can be distinguished. The micro-simulation models like MASTER, they consider that urbanization can be the outcome of multiple individual choices within a population. I would say that such models are the most difficult, and sometimes they're also related to so-called fuzzy models, so to the models where we have a huge stochastic component, because individual choice is something that's well, also very diverse and very quite challenging to model, to project. And models based on such tools as cellular automata, again like CLUE or CLUE-S, which we discussed before, they consider urbanization based on the suitability factor. So they consider that if an area is the most suitable for urban expansion based on the combination of environmental, social, economic, and neighborhood factors, this area becomes urbanized. Here you can see a review of some models, also from the paper by Alberti in 1999. And here you see some examples of the models which are purely urban model, like here IRPAD, where the population, employment, housing, and land use are considered, and you see different approaches like network equilibrium or Monte Carlo microsimulation, which are used to model those blocks or those subsystems. All the environmental models like Century, which we mentioned before, Century, the classical model for carbon cycle, and here we see also the time and dynamic and the space, the spatial resolution, and the way human factors are included. And similarly, the image, which is more a global model or some others. Okay, and now let's move to the final part where we will describe particular examples of models for different urban components, starting from the climate and the atmosphere, and then the water, and then the soil. So basically, if you understood everything before, then the last part shall be just an illustration how these frameworks, assumptions, driving factors are implemented for particular ecosystem components. If you misunderstood something, then probably you would have some difficulties, so do not hesitate to ask. Okay, let's start from modeling urban atmosphere, and more particularly urban heat island. To begin with, urban heat island is a mesoclimatic anomaly which is visible as higher temperatures, high air temperatures, but also soil temperatures in the central and more built up areas in comparison to the suburb or to the natural areas. For the first time, it was described more than 150 years ago, almost 200 years ago for London. But since then, it was shown many times for many megapolises in the world, and I would say almost any city is exposed to urban heat island. And of course, modeling urban heat island in time, and especially in space, is important for environmental issues, but also for some economical issues, for instance, to consider it for the central heating issues, etc. How can we map urban atmosphere and urban heat island? First of all, regarding the incoming data, remember that for each model we will consider this framework: incoming data, model drivers, and spatial levels and model outputs. So the incoming data are the meteorological data. Usually it's air temperature and air humidity, which are collected from the meteorological stations. There are lots of limitations here as well, like most of the meteorological stations are not inside the cities, usually outside the cities, and that's why they are not fully representative for urban climate. But there are also some ways. For instance, in Moscow, there are stations of air quality control which also measure temperature, and they are inside urban areas, and the data from those stations is also used to feed the models. And we also consider soil temperature, soil moisture, wind speed, wind direction, and many special data like surface, for instance, etc. For the model drivers, we have physical parameters, mainly parameters of the ground surface, like roughness or elevation, albedo, etc. Bioclimatic drivers, like zonal traditional temperatures, the bioclimatic zone. Anthropogenic factors like population, transport, the spatial structure of the city, etc. And location and time, as soon as urban heat island model, as any climatic model, has two dimensions, temporal dynamic and spatial dynamic. So we need to know the temperature in a particular place in a particular time. In terms of the levels, we can go to the boundary level, to the canopy layer, or to the surface layer, so from top to bottom. And of course, the accuracy will decrease from the boundary to the surface, but at the same time, the let's say the area covered by the model will increase. These are possible modeling results. For instance, we can talk about the temperature maps, which are the most typical outcomes, and these are the maps generated by our colleagues from the meteorology group, where you can see the heat wave in Moscow 2017. Also, it could be temperature profiles when we see how temperature changes with the height. Usually such data is common based on the multi-layerness assumption. And even 3D models, if we have enough accurate 3D spatial data, for instance, with the different expositions of the roofs, etc., we can see how the temperature will differ. Okay, that was an example of the temperature air quality model. Now we can move to the water model, for instance, talking about the surface water dynamics. So we do not talk about water quality, which is also possible, but this example is about water quantity. And the main idea behind such model is that we have the incoming water flux as a precipitation, which gets to the surface and then can be distributed in several directions, as filtration can go down, as the evaporation or evapotranspiration can go up, and the surface runoff, which is the lateral removal of the water, mainly following the elevation. So altogether, all three occur, and depending on the surface, some of them can dominate. For instance, if we talk about the sealed soils, like roads, of course, filtration will be minimum, and surface runoff will be dominated. And if we talk about open spaces, like grasses, lawns, trees, then filtration and evaporation will be higher and surface runoff will be less. When we deal with the flood flooding, then flooding is usually mainly driven by the surface runoff, especially when the rainfall is very intensive. So the drainage system can be overloaded, and in this case flooding becomes an issue. So most of the flood models are considering surface runoff and precipitation, and keep in mind filtration and evaporation as the processes. This is an example of flood model described by Lichtenberg in 2010. It was done for Netherlands, where flooding is a especially important issue since the elevation of most of the country is below sea level. So they mainly are protected by dikes, and if the surface water level gets higher, then the risks of flooding are very high and the possible outcomes are very negative. So the incoming data here can be the water layer and incoming water flow. So how much water do we have and how much water will be incoming per grid from precipitation, for instance, or from elsewhere. Then for each grid, we consider the capacity of grid, which is the difference in elevation. So basically, we assume that the water, the surface runoff moves from the top level, from the top of the hill to the bottom of the hill, and that's why the elevation is the main information. Basically, these models usually work the digital elevation model, DEM, as the main income. And the model drivers, again, can be physical, so we need to know the elevation characteristics, soil texture, soil filtration coefficients, bioclimatic, like precipitation and evaporation, and anthropogenic, first of all, land use and land cover. And again, location and time, because that's the spatial temporal model. And these are the possible outcomes. So we can have some graphs which can illustrate, for instance, the water depth per some particular area in time, or we can have the map which will show the flood risks at the special area, etc. Actually, both are necessary to project some kind of measures to mitigate the flood risks or to take when the flooding occurs. Urban vegetation, another case for landscape designers, for generally people working with landscape agriculture, may be the most interesting. So when we talk about urban vegetation, we first of all keep in mind number of functions and ecosystem services that can be provided by urban vegetation. And they are many. Some of them are more conventional, like carbon sequestration, microclimate support, primary energy production, water uptake, air quality control, preventing soil from erosion, supporting biota, etc. So these services which are clearly expected from any vegetation, urban or natural. But when we talk about urban vegetation, we have some specifics where some factors, but at the same time, some services are more human-oriented. For instance, we need a sanitary function or a recreation function, an aesthetic function, food safety, etc. So these services are what is expected to be modeled by the urban vegetation models. There are lots of ways to model urban vegetation. I will illustrate you several. And let's begin with the models based on the remote sensing data. So these are the special models which consider remote sensing data, data from satellite images, data from drones as the main incoming data. So the data which can be used include the geometry of the vegetation, of the canopies, their height, their, let's say, the space covered by the leaf area index, etc. Their condition, sometimes like weak or healthy, their biomass, etc. The model drivers also could include some physical components, soils, climate, temperature, and anthropogenic components, including the pollution, also location and time, to make the model spatially temporal. And the spatial levels, we can talk about the canopy level or about the region level. This is an example of a model which characterizes the geometry of the forest canopies in woodlands. So basically, based on the LiDAR measurements, the 3D models of the particular trees are calculated. We have the coordinates of each tree, and we reconstruct the canopies based on the elevation models, highly precise elevation models, and we can use it to estimate the biomass growth, for instance, or some other parameters. This is a more simple, but at the same time, probably more broad model. Even not a model, I would say, like the modeling tool, modeling exercise. It is called Specifiant. It can be available at the webpage Green Urbs, which was the consortium, the scientific consortium supported by the Cost Action European project. And this consortium aimed to analyze the ecosystem services from urban green infrastructures. So in this model, you can select well, first of all, you can select your location. I think one of 30 or so European cities. And you can also prioritize the ecosystem services that you expect from the green infrastructure. For instance, pollution removal, and you can also rank which pollution, first of all, you are aware of. And then also allergenicity, emissions, VOC emissions, carbon storage, etc. So you select several ecosystem services. You also put the range of the height of the trees, put the location, and in result you get the list of species that can be used for this purpose, and each species has the values how each of the services can be performed from the scale from 1 to 5. So in this regard, you get some idea not only on the ecosystem services provided by particular trees, but also on which trees can be used to obtain such ecosystem services, which makes a lot of sense for urban planning, for instance. Following this concept and actually partly overlapping to the previous case, let me introduce you an I-tree model or I-tree eco model, or more precisely, it's even the set of models, which also focus on the estimating ecosystem services of urban trees based on their characteristics, their location, their species, on their dB, which is diameter at the breast height, and also on data which characterize pollution risks and climate data. The model was developed by David Novak from USDA, and now this model is quite well known. You can find a particular web page for I-tree eco, and again there are a set of models focused on some particular services like climate, for instance, or water, or on some particular cases. This is how the model process looks like. So first you have the tree inventory following some algorithms. So you collect data on the trees, on their location, on their height, geometry, etc., etc. You have some user manual to do it. And you also provide some data for cost-benefit analysis. For instance, the costs for electricity or for their air purification from dust, etc. And what the model does is it estimates the ecosystem services based on this on the tree inventory data and on economical data you provided, and make some balance. So how much will cost to create the urban infrastructure and how beneficial will be such an infrastructure regarding the ecosystem services can provide. For instance, we had some experience when we did not use the I-tree model, but instead we used some equations to calculate, for instance, the potential of urban environment to capture dust or to increase biomass, etc. So you see that basically behind each of the factors, each of the services, like air pollution flux calculation or canopy resistance calculation, you have a formula which relates the service to some measurable parameters. For instance, the canopy resistance calculation is estimated as a function of stomatal resistance, mesophyll resistance, soil resistance, which is usually fixed to a particular value, and cuticular resistance, etc. This is how the I-tree web page look like, and these are the list of I-tree tools. We mainly deal with I-tree Eco. It's kind of the full scale, but there's also I-tree Hydro, I-tree Trees, etc. Yeah, which depend again on the scale and on the particular goal. And these are kind of results which are also available from the web page, so you can get some examples. This is, for instance, the example I think for Wales, or for Britain, something there. And yeah, there were not only the let's say the data sets with a particular values, also monetary values for different scenarios, but also the maps which do the ecosystem services and some kind of bar plots which compare how different trees, for instance, trees of different species or different condition, can provide the services. Okay, and finally an example about urban soils. Urban soils generally is a quite a interesting topic due to its complexity, heterogeneity, etc. And basically, soils are considered to be a function of 5 soil forming factors: climate, biota, relief, burn material, and time, as was proposed by Dokuchayev also more than 100 years ago. And when we talk about urban environment, and anthropogenic factor is also added. We can expect direct and indirect effects of anthropogenic factor on urban soils. Direct are related to soil seeding, pollution, soil construction, and indirect are about changes of the soil forming factors like climate, for instance, and or terracing of the relief, etc. And these are some models implemented for urban soils. This is, for instance, the Hydros model. Hydros model is a model for projecting of the water, heat, and soluble fluxes in soils and soil constructions. So it basically the model based on soil physical properties. And this Richards equation is the theoretical background of Hydros. So you consider soil as a one or multi-layered environment, and you need to know the incoming and outgoing flux Q and the difference of the parameter. Could be temperature or water or concentration of the soluble parameter. So when we talk about water fluxes, and water fluxes are the most typically modeled for Hydros, because even if you deal with solubles, you anyway need to know the water fluxes. As a rule, the main incoming data is the water retention curve, which is the relationship between the water potential and the soil moisture, approximated by one of the equations, usually by one Genuchten equation. And the parameters of this Van Genoochten equation are the incoming data for the hydros. These are water retention curves approximated by Van Genoochten equation, and this is the equation. While here you see different curves for sand, BC is the bulk sand, loamy soil, valley peat, and typical Chernozem. You see that they are very different, although the shape are similar, but the difference between substrates is clear. And for instance, we see that for the valley peat, the water holding capacity is the highest, could be more than 130%, whereas for sand it's just 21, etc. So this data is obtained from the experiments. We do it by the equilibrium centrifusion approach. There are other ways to get such data, and the parameters are extracted. And these parameters are used to feed the hydros model provided by the PC progress system, quite a complex multi-step model where you can define the depth of the layer and texture, precipitation, and the root uptake, so many parameters. And at the end of the day, you get something like this. For instance, you can see the temporal dynamics of water fluxes, or if you work with a 2D, 3D model, you can also see the water storages per layer, or you can project how the water will be filtered or evapotranspirated for a particular case. Okay, this is modeling carbon or nutrient cycles, which are also very classical, and this is basically one of the models, can be one of the examples to illustrate the question which was asked. This is the, I think this is ROT-C model by Parton and Ellis, developed at the Rotterdam, based on the data from Rotterdam experimental station. And you see that it looks kind of complicated because the model subdivides soil and biomass in many compartments, and for each compartment, like soil organic matter, for instance, and soil organic matter also is subdivided in active or slow or passive, depending on how fast it can be mineralized, and the mineralization in each compartment depends on the CN ratio. So, and CN ratio basically drives the microbial activity. So there are quite a number of processes here, but they all at the end of the day show how organic matter which gets to the system from humification of the plant residuals can be, what happens with them, yeah, which can be stored in soil carbon stocks, for instance, or it could be turned over and released as CO2, and what is the time periods for that, etc. So this type of models, again, the ROT-C, Century, DaySen, Rommel-Hume, and LPJ, some other models of carbon cycle, they basically have this or similar structure. For them, incoming data would be soil chemical properties. First of all, carbon and nitrogen, they are crucial, but also could be some more data, pH, nutrients, etc. Soil physical features, soil microbiological properties could also be, and also the management data. For instance, many of those models, they change depending on irrigation or fertilization, to say nothing about urbanization. As for the model drivers, we have the bioclimatic parameters like precipitation or air temperature, anthropogenic parameters, and also location and time if we put it into the space, because for instance, Century can also work just for a profile. And these are possible modeling results, which can be the profile distribution or some temporal dynamic, in this case, the dynamic of soil moisture, or the maps we deal with the spatial analysis and if we address these equations to some special background. Okay, that's pretty much it for the lecture. I see there are some questions, so I will move to the questions. But before, let me announce that if you need some more information, I recommend you to visit our Research Center webpage. There are lots of data on technologies and on some information on our current research. And talking about the educational activities, also from this website, you can get an access to the full version of the Modeling Urban Ecosystem course, which is a massive open online course for, I think, 70 or 100 hours, so pretty long, which is available from open learning system and from some other systems. So what was today, it was kind of the summary from this course. If you get involved, you would like to learn more, please go there. Okay, and now let's check what are the questions. And okay, I think I saw something in chat or not, because or did I misunderstand this? What did we get anything? Because
we have only one question from Abhishek Pandey.
Okay, can we combine features of two or more models to construct a hybrid model? Yeah, of course, that depends. Well, again, theoretically it's possible. Technically, it depends on the modeling skills. But for instance, combination of spatial models and temporal models are very typical. For instance, the century model, which is the process-based model of carbon fluxes, is quite often combined to the land use change spatial models, because we can see the particular carbon turnover for cropland and for the forest, for instance. And as soon as we can model at the beginning how which area will be occupied by forests and which area will be occupied by croplands, then we can use century model for this changed land use, and etc. I mean, the models are the tools and the number of equations, so you can use them the way which is the most appropriate for you. But that's the theory. Technically, yeah, it depends on are you available to do it, is the script open, etc. And that's of course quite a long story to be discussed. Okay, if there are any other questions, please ask. Otherwise, you can probably address them further on to the email or elsewhere. And I pass the floor to Vlad.
Thank you very much, Professor. I think I don't see any questions in the chat, and I don't see any hands up. So I think that we don't have.
So we make a test now, huh? To check how people understood the lecture and give some marks. Yeah, it's a joke. We're not going to. Okay, then thank you for your attention, and again, feel free to continue learning modeling urban ecosystems via the resources I recommended or via the other resources. So that's a nice and promising topic of research and studies.
Thank you very much, Professor. Dear students, if you have any questions to Dr. Vasenev or to me, you may address it to us by my email, or you may use this chat to ask your questions. If you don't have any questions, I want to appreciate Dr. Viacheslav Vasenev for the very interesting lecture, and thank you very much for your time, for being here with us, for participating in our Autumn School. So dear students, if you don't have any question, Please let's be in touch via mails, and see you next Saturday. Next Saturday, the session by the veterinary medicine will be held. So please join us and please ask your questions via my mail. Okay, thank you very much. I wish you a nice day or nice evening, and see you.